The ground you stand on was born from fire. Our continents have a hidden architect, a force of unimaginable power that has been shaping the world for billions of years. This is the story of the planet that breathed fire, and by the end, you will see the very map of our world in a completely new light. We will uncover how a planet of molten rock forged the first land, why entire mountain ranges are the scars of ancient collisions, and what mysterious engine deep within the Earth continues to rebuild the continents even today. The ground beneath us feels permanent, but what if its entire history is a lie written in volcanic stone? 4.5 billion years ago, our world was a vision of hell. There were no continents, no deep blue oceans, only a global ocean of churning, incandescent rock. This was the Hadean Eon, a time named for the underworld itself. The young Earth was a cauldron of unimaginable heat, a remnant of the violent collisions that built it, and it was this very heat that became the driving force for everything to come. Deep within that molten sphere, a great sorting began. Heavier elements like iron and nickel were pulled by gravity toward the center, forming a dense metallic core. Lighter, buoyant minerals slowly rose to the surface, creating the first thin skin of solid rock. This was the birth of our planet's layered structure, the core, the mantle, and that fragile crust. This process, known as differentiation, was the most important event in Earth's early life. It established the planet's internal engine, a heat machine that would run for billions of years. And as this engine churned, it began to exhale. The planet itself breathed out, a process called outgassing. From countless volcanic fissures and vents, the Earth released immense quantities of water vapor, carbon dioxide, nitrogen, and other gases that had been trapped within its molten interior. Over eons, as the planet's surface slowly cooled, that water vapor condensed into clouds and then fell in torrential, global rains, gradually filling the basins to create the first true oceans. The gases remained, forming a primitive but life-giving atmosphere. This chaotic, fiery beginning was not just a prelude, it was the essential first chapter. That initial separation of the planet into layers created the thermal imbalances that drive the mantle's slow, powerful convection currents to this day. The stage was now set, the engine was running, but the first true continents, the foundations of our modern world, were still waiting in the wings, ready to be forged from the very rock of that primordial sea. This entire process relies on a single, magnificent engine. Deep within the Earth, a vast heat machine is perpetually churning. Picture a pot of thick soup simmering on a stove. The heat at the bottom causes the liquid to rise, cool at the surface, and then sink back down, creating a continuous, rolling motion. Now, imagine that on a planetary scale, with solid rock flowing over millions of years. This is the force of mantle convection, the great driver of our restless planet. This slow but immense circulation is the power behind a revolutionary idea that once seemed absurd, the theory of plate tectonics. Our world's outer shell, the lithosphere, is not a single, unbroken eggshell. It is a cracked mosaic of gigantic plates, each one floating and drifting on the hotter, softer rock of the asthenosphere below. These plates are in constant motion, jostling like rafts on a slow-moving river of molten stone. Where these plates pull apart, new crust is born from rising magma. Where they collide, one plate can be forced beneath another in a colossal grind, or they can crumple upwards, forging mighty mountain ranges. It is precisely at these violent, dynamic boundaries that the planet's fire-breathing nature is most visible. The ring of fire around the Pacific Ocean, the volcanic islands of Hawaii, the immense Himalayas, all are direct results of this ceaseless tectonic dance. This grand, unifying framework of geology explains not just earthquakes and volcanoes, but the very creation and destruction of land itself. To understand how our continents were built, we must first listen to the steady, powerful rhythm of this internal engine. But this grand tectonic engine has a second, more mysterious partner in shaping our world. Far from the grinding edges of the tectonic plates, in the seemingly stable hearts of continents and oceans, another force is at work. Imagine a colossal pillar of superheated rock, a thermal plume rising from the very border of the Earth's molten core and the lower mantle. This is a mantle plume, a deep Earth blowtorch aimed directly at the underside of the planet's crust. When such a plume reaches the surface, it creates a volcanic hotspot, a persistent and intensely active vent. The Hawaiian Islands are a perfect, living example of this phenomenon. They are not located at a plate boundary, but right in the middle of the vast Pacific plate. The plate slowly drifts northwestward, while the stationary hotspot beneath it burns a hole through the crust, building a chain of volcanoes one after another. The island of Hawaii, with its active volcanoes, currently sits over the hotspot, while the older islands to the northwest are the extinct remnants of this same process, a timeline of volcanic activity written across the ocean floor. The power of these plumes is staggering. They do not just create island chains, they can trigger cataclysmic volcanic events known as large igneous provinces. These are titanic outpourings of lava that can cover millions of square kilometers in a relatively short geological time. When such an event occurs, it floods the landscape with basalt, adding a massive new layer of crust to the continent. This is a fundamental mechanism of continental growth. While plate tectonics recycles and reshapes crust, these deep-seated mantle plumes provide vast injections of new material, literally building the continents from the bottom up. This hidden process provides a crucial answer to how our landmasses have gained their volume and complexity over billions of years. 300 million years ago, the world map would have been a study in solitude. Nearly all of Earth's landmasses were welded together into a single, colossal continent called Pangea, a vast supercontinent surrounded by a global ocean. This was not a unique event, but merely the most recent act in a grand, repeating drama known as the Supercontinent Cycle. This cycle is the planetary pulse of plate tectonics, a rhythmic beat that sees continents gather together, only to be torn apart again over hundreds of millions of years. Think of it as the Earth's slow, majestic breath. The continents inhale, drawing together into one massive landform, and then they exhale, scattering across the globe. But what force could possibly shatter such an immense entity? The answer lies in the very engine that built it. When a supercontinent like Pangea forms, it acts like a giant, insulating blanket stretched across the planet's surface. This blanket traps the immense heat rising from the mantle below. With the escape route blocked, temperatures beneath the continent begin to soar, building pressure like a pot with a tightly sealed lid. Eventually, the mantle's heat can no longer be contained. It forces its way upward, warping the continental crust and unleashing catastrophic volcanic fury. This is exactly what happened to Pangea. Its breakup was heralded by one of the most volcanically violent periods in Earth's history, an event known as the Central Atlantic Magmatic Province. Fissures thousands of miles long cracked open across the land, flooding the landscape with enough lava to bury entire countries. This was the divorce decree that split the Americas from Africa and Europe, an unstoppable thermal upheaval that permanently reshaped the world. But the cycle does not end with the breakup. These newly liberated continental fragments, carrying the scars of their birth, begin their slow, solitary journeys across the globe. They are not aimless wanderers, they are destined to collide again. When these drifting landmasses meet, they lack the space to subduct gracefully beneath one another. Instead, they crumple, their edges folding and stacking into the roots of new mountain ranges, forging new continental configurations in a collision that writes the next chapter of the planet's story. This relentless cycle of assembly and dispersal has happened multiple times in Earth's deep past, with supercontinents like Rodinia and Nuna coming together and breaking apart long before Pangea ever existed. Each breakup seeds the ocean floor with new land, and each collision welds that land onto the growing continents, adding another layer to their complex, fiery history. This fundamental difference in density is the key to our planet's enduring land. Oceanic crust is heavy and dense, forged from dark basalt at mid-ocean ridges, and destined to sink back into the mantle at subduction zones in a cycle that rarely lasts more than 200 million years. Continental crust, however, is built from a different recipe. It is lighter, buoyant, and composed of rocks like granite, which are rich in silica. This buoyancy is its salvation. When a continent meets a subduction zone, it does not easily dive into the abyss. It resists, it crumples, it persists. This is why we can find rocks on the surface today that are over 4 billion years old, time capsules from the planet's fiery infancy. These ancient rocks form the hearts of the continents, the cratons. Imagine a craton as the continental seed, an unbelievably stable and thick piece of crust that has survived virtually unchanged for eons. They are the foundations upon which everything else is built, the unshakable cores of every major landmass you see on a map. But how did these seeds grow into the vast continents we know? The process is a slow geological assembly line. At the edges of these ancient cratons, subduction zones were constantly active. As oceanic plates dove beneath the continental margin, the intense pressure and heat melted the rock, fueling massive chains of volcanoes offshore. These volcanic island arcs, much like modern-day Japan or the Aleutian Islands, were also made of relatively light rock. Over millions of years, as the tectonic plates continued their slow dance, these island arcs did not subduct. Instead, they collided with and were welded onto the edge of the waiting craton. This process, known as accretion, added new land piece by piece, fragment by fragment. It is a story written in stone, a gradual accumulation of volcanic terranes that expanded the continents outward from their unyielding cores. This is how the continents achieved their permanent presence. They are not static slabs, but ever-growing, complex mosaics, assembled over billions of years from the planet's own fiery exhalations. This slow, persistent growth created stable, elevated platforms high above the recycling depths of the ocean floor, setting a stage unlike any other in the solar system, a stage upon which life itself could finally take root and thrive. A volcanic island chain like Japan is more than a geological spectacle, it is a foundational workshop. These arcs of fire and rock are the very factories where new continents are forged. The process begins deep beneath the ocean, where an oceanic plate bends and plunges into the mantle. As it descends into unimaginable heat and pressure, it carries with it something crucial: seawater locked within its minerals. This water is then cooked out of the sinking plate, rising into the overlying wedge of mantle rock. Water acts as a powerful flux here, drastically lowering the rock's melting point. Solid rock that would otherwise remain stable begins to melt, generating vast chambers of buoyant magma. This newly born magma begins its slow ascent, punching its way upward through the crust until it erupts at the surface in a dramatic line of volcanoes. The lava that flows from these volcanoes is special. It is not the dark, dense basalt of the ocean floor, but a lighter, silica-rich rock called andesite. This composition is a crucial intermediate step, a literal chemical bridge between the heavy basalt of the oceanic crust and the buoyant granite that forms the core of our continents. This is the primary production line for new continental material, but raw material is not yet a continent. The final step is assembly. As the tectonic conveyor belt continues its slow, relentless motion, these volcanic island arcs are destined for a collision. They are pushed toward the waiting edge of an existing continent. They cannot be subducted as they are too buoyant. Instead, they are scraped off, crumpled, and welded permanently onto the continental margin. This process, known as accretion, is how continents physically grow. Each volcanic arc that collides is another piece of land added to the map, another expansion of the continental shelf. Over hundreds of millions of years, this relentless cycle of subduction, melting, eruption, and collision has assembled the sprawling continents we recognize today, piece by fiery piece. The western mountains of North America hold a secret in their very bones. They are not a single, unified range born from one event, but a vast geological mosaic. Their history is a story of travel and collision, written in the language of stone. These mountains are the result of a process called accretion, the slow-motion stitching together of continents. Imagine the tectonic plates as colossal conveyor belts, slowly drifting across the planet's surface. Riding on these plates are smaller landmasses, known to geologists as terranes. A terrane is a distinct fragment of crust with its own unique geological fingerprint, a history entirely separate from the continent it is approaching. It might be an ancient volcanic island chain, a submerged plateau of basalt, or a sliver of crust scraped from the ocean floor. These terranes are too buoyant, too light, to follow the dense oceanic plate down into a subduction zone. They are the geological survivors. When their tectonic raft carries them to the edge of a waiting continent, they cannot be consumed. Instead, they collide. The force of this impact is immense, crumpling the leading edges of both the terrane and the continent. The terrane is scraped off, smashed, and permanently welded onto the continental margin. This is accretion in action, the literal addition of new land. The coast of California, Oregon, and Washington, and the rugged interior of British Columbia and Alaska are all spectacular examples of this process. Much of this landscape is a complex collage of dozens, even hundreds of these accreted terranes, each one a lost world sutured into the growing continent. Over hundreds of millions of years, this relentless geological stitching has built out coastlines, expanded continental shelves, and dramatically increased the total land area available for life. Our modern continents are not monolithic blocks, but intricate tapestries woven together from countless journeys across the ancient Earth. 2.5 billion years ago, a quiet revolution began in the planet's crust. The very same volcanic chains that were building the continents began to alter the air itself. As these mountains rose, their freshly exposed rock underwent a process called chemical weathering. Rain, slightly acidic from the carbon dioxide in the atmosphere, reacted with the volcanic minerals, slowly breaking them down. This chemical reaction did something remarkable. It began to release free oxygen into the air. For the first time in Earth's history, oxygen was not just a fleeting byproduct of life, but a geological force. In the sunlit surface waters of the oceans, another revolution was underway. Microscopic cyanobacteria were perfecting the process of photosynthesis, consuming carbon dioxide and releasing oxygen as their own waste product. For eons, this oxygen was immediately mopped up by the vast amounts of dissolved iron in the seawater, rusting on a planetary scale. The proof is locked in stone, in beautiful banded iron formations, layers of red and gray that represent the slow, rhythmic breathing of the ancient Earth. But the balance was tipping. The dual engines of geology and biology were pumping out oxygen faster than the natural sponges could absorb it. The atmosphere reached a critical threshold. This was the Great Oxidation Event, a point of no return that permanently changed our world's chemistry. This was a climate catastrophe for the anaerobic life that had dominated the planet, but it was the single most important event for our own future. It cleared the way for oxygen-breathing organisms and created the protective ozone layer that shields life from the sun's harsh radiation. The breathable air we depend on is a direct legacy of the planet's fiery geology, a testament to how the construction of the continents and the creation of a habitable world are one and the same story. This power to build is also a power to destroy. The same deep-seated mantle plumes that construct continents can, in their most violent expressions, trigger global catastrophe. The evidence for this lies in a stark and terrifying landscape, the Siberian Traps. Today, this is a vast, layered plain of black rock in Russia, covering an area larger than Western Europe. But 250 million years ago, it was the epicenter of hell on Earth. This was not a traditional volcano with a single peak, but a flood basalt eruption. Imagine the crust of the Earth cracking open along fissures hundreds of miles long. From these wounds in the planet, lava did not merely flow, it flooded the land in waves of incandescent rock, layer upon layer, for hundreds of thousands of years. The volume of lava was so immense it is almost impossible to comprehend, enough to bury the entire surface of the United States under half a mile of solid rock. The creation of the Siberian Traps coincided almost exactly with the most severe crisis in the history of life, the Permian-Triassic extinction. This was not a slow decline, but a rapid, brutal collapse of the global biosphere. Nearly 90% of all marine species vanished forever. On land, 70% of vertebrate families were wiped out. The link between the eruptions and the extinction is written in the chemistry of the rocks and the fossils, or rather, the lack of them. The initial devastation came from the lava itself, incinerating everything in its path and releasing clouds of ash and toxic gases that choked the skies. But the true killers were the invisible gases. Enormous quantities of sulfur dioxide billowed into the upper atmosphere, reacting to form acidic aerosols that blotted out the sun, triggering a brutal volcanic winter. Then, as the ash cleared, the longer-term horror set in. The eruptions released staggering amounts of carbon dioxide, a potent greenhouse gas. The planet's climate, shocked by cold, now swung violently in the opposite direction, plunging into a rapid and extreme global warming. The oceans absorbed much of this carbon dioxide, becoming so acidic that they dissolved the shells of countless marine organisms. The warming also stripped the oceans of oxygen, creating vast dead zones where nothing could survive. To complete the assault, the volcanic halogens released likely shredded the protective ozone layer, allowing harmful ultraviolet radiation to scorch the land. This was a planet-wide assault on every front, a cascade of disasters all tracing back to that single, fiery source. The very force that built our world's foundation also possesses the power to nearly wipe its slate clean, a stark reminder that the planet's creative and destructive forces are one and the same. A perfect arc of fire and fury encircles the Pacific Ocean today. This is the Ring of Fire, a horseshoe-shaped belt that runs for 25,000 miles, tracing the edges of the Pacific Plate. From the Andes to the Aleutians, from Japan to New Zealand, this is the most geologically active place on our planet. It is a living, breathing demonstration of the very processes that built our world. Here, the immense Pacific Plate is slowly but relentlessly diving beneath the surrounding continental plates in a process called subduction. It is along these grinding, colliding margins that the planet continues to exhale its fiery breath, building new continental crust right before our eyes. The Andes mountain range is the ultimate testament to this ongoing creation. This colossal wall of rock is not a relic of the distant past. It is actively growing, pushed higher by the constant subduction of the Pacific Plate beneath South America. Each major earthquake is not just a tremor, it is a lurch in the mountain's upward journey. Every volcanic eruption along the chain is a delivery of new, molten rock from the depths, material that will cool and solidify, becoming a permanent part of the continent. This is the same fundamental mechanism that has operated for billions of years. The Ring of Fire is our real-time laboratory, a place where we can witness the ancient planet-shaping forces in their raw, untamed state. It shows us with absolute clarity that the construction of our continents is not a finished project, but a continuous, dynamic, and powerful process that continues to reshape the world beneath our feet. Deep beneath the soaring peaks of the Sierra Nevada, there is another mountain range entirely, one that never sees the sun. It is a hidden architecture of stone, a foundation of colossal proportions made not from a single rock, but from a single, solidified event. These are granite batholiths, the true backbone of the continents. To understand them, you must picture the process not as an eruption, but as an intrusion. Above a subduction zone, where an oceanic plate dives into the mantle, water is squeezed from the sinking rock. This water acts like a chemical key, unlocking the melting point of the overlying mantle and generating vast quantities of magma. This newly formed magma is buoyant, and it begins an epic, slow-motion ascent, pushing its way upward through miles of solid crust. It does not break the surface. Instead, it finds a home pooling in enormous underground reservoirs known as magma chambers. Here, insulated by thousands of feet of rock, the magma has all the time in the world. It cools with an almost unimaginable slowness over millions of years. This gradual cooling is the secret to its strength. It allows large, interlocking crystals of minerals like quartz and feldspar to form, creating the hard, coarse-grained, and incredibly resilient rock we know as granite. While the volcanoes above might erupt and erode away, these hidden granite giants remain. They are the unyielding anchors, the deep roots that stabilize the continents against the relentless forces of erosion and tectonics. When the softer rock above is eventually stripped away by wind and water, the batholith is exposed, standing as a stark, majestic range, a testament to the power of slow, patient fire. This is how the planet forges its most durable land, not in a flash of volcanic fury, but in the deep, quiet crucibles of the crust. Every ocean has a lifespan, a dramatic story from birth to death. This grand narrative is known as the Wilson cycle, a planetary rhythm that continuously remakes the world map. The cycle begins with a continent under stress. The immense heat trapped beneath a supercontinent, as we saw with Pangea, eventually causes the land to bulge and fracture. The crust stretches thin, creating a massive rift valley, a wound in the continent that slowly pulls wider. Magma rises from below, flooding the valley floor with new basalt. This is the birth of a new ocean basin. Today, we can witness this infant stage in the Red Sea, a narrow seaway that is actively widening as the Arabian Peninsula slowly drifts away from Africa. As the rift continues to stretch, a true mid-ocean ridge forms, an underwater mountain range where two tectonic plates are pulling apart. Here, at this divergent boundary, new oceanic crust is constantly forged from upwelling magma, cooling to form the solid rock of the seafloor. This new crust pushes the plates apart, causing the ocean basin to grow wider and wider over millions of years, much like the Atlantic Ocean is doing today. But this expansion cannot last forever. The destiny of every ocean is to close. The turning point comes when the dense, heavy oceanic crust, now old and cold, begins to founder. At a continental margin, it starts to sink back into the mantle, initiating a subduction zone. Once this process begins, the ocean's fate is sealed. The ocean basin stops growing and starts to shrink, consumed by the very mantle that created it. The final act is one of colossal impact. As the ocean closes, the continents on either side are drawn inexorably closer. With the oceanic plate entirely consumed, the two continental landmasses finally meet. They cannot subduct, they are both too buoyant, so they collide. The force of this continental collision is beyond comprehension. The land crumples, folds, and stacks upon itself, thrusting upward to form a new mountain range that marks the suture between the two former continents. The Himalayas, the highest mountains on Earth, are the spectacular result of this process, the ongoing collision between India and Asia. The ocean that once separated them, the Tethys Ocean, is gone, its crust recycled into the planet's interior. This completed Wilson cycle welds the continents together, creating a new, larger landmass and setting the stage for the entire process to begin again. The ground we walk on is not just land, it is a chapter in an endless story of oceans rising and falling, written by the patient, fiery breath of the planet. Without water, our planet would be geologically silent. The continents would be barren, the mountains low, and the ring of fire a circle of embers. Water is the secret ingredient, the invisible catalyst that transforms a slow grind into a creative fire. This life-giving substance becomes a geological agent when an oceanic plate begins its final descent into the mantle. That plate is not dry, it is soaked. For millions of years, it has sat on the ocean floor, its basaltic rock becoming riddled with fractures that absorb seawater. It is also covered in a blanket of wet, clay-rich sediments, the accumulated dust of ancient marine life and eroded continents. As the plate bends and plunges, it carries this entire reservoir of water with it, locked in its minerals and clinging to its surface, diving toward the planet's interior. This journey is a one-way trip into an oven of immense pressure and scorching heat. At a depth of around 100 kilometers, the conditions become so extreme that the water can no longer remain trapped within the sinking slab. It is cooked out, forced from its mineral cages in a process called dehydration. This released water does not simply vanish. It rises upward, percolating into the wedge of solid mantle rock that lies directly above the subducting plate. And here, water performs its most vital trick. It acts as a powerful flux. The mantle rock at these depths is incredibly hot, but its melting point is also phenomenally high. When the water infiltrates this hot rock, it drastically weakens the chemical bonds between the mineral grains. In essence, the water lowers the rock's melting point, turning what was a solid into a partial liquid. This is the genesis of the magma that will feed the volcanoes of the Ring of Fire. This process, known as flux melting, is the primary reason we have chains of volcanoes tracing the edges of continents. Without that descending water, the mantle wedge would remain largely solid, producing only a tiny fraction of the magma we see. The type of magma created is also a direct result of this watery process. The melting is not total. It selectively targets minerals with lower melting points, which are richer in silica and other lighter elements. This generates a magma that is more viscous and gas-rich than the fluid basalt of mid-ocean ridges. This is the recipe for andesite and granite, the very stuff of continents. It is also the recipe for explosive eruptions. The high water content turns into steam as the magma rises, building immense pressure until the volcano can no longer contain it, resulting in the catastrophic blasts that define the Pacific Rim. The planet breathes fire, but it is water that gives that breath its creative power, forging the land itself from the deep, wet darkness of the Earth. The mystery of the first continents lies locked within the oldest rocks on Earth. 4 billion years ago, our planet was a vastly different world, a hotter and more violent place where the very rules of geology might have been different. The formation of the first permanent land, the cratons, is a puzzle that challenges our understanding of the planet's fiery youth. Geologists call the ancient rocks that form the cores of these cratons TTG suites, a complex name for a unique blend of minerals that is the primordial stuff of continents. How did this specific rock type form? The leading theory points to an early, more chaotic version of the subduction we see today. In the intense heat of the Archean Earth, the basaltic crust may have grown so thick and heavy that it began to sink in massive, dripping folds rather than in the neat, linear plates of the modern world. These sinking blobs of ocean floor would have plunged to incredible depths where the immense pressure and heat caused them to melt. This partial melting, a great sorting of elements deep within the Earth, is what likely cooked the first TTG magmas. These buoyant magmas then rose, intruding the primitive crust and forming the seeds of the very first protocontinents. This was not the slow, steady growth we see now, but a more violent, episodic birthing of land. Solving this ancient mystery is crucial, for it marks the pivotal moment our planet ceased to be a water world and began building the stable, enduring platforms that would one day allow life to flourish on dry ground. These same mountains that build our world also hold the key to its climate. The volcanic chains that forge continents do more than just create land. They act as the planet's long-term thermostat through a magnificent process known as the carbon silicate cycle. This cycle begins with a deep geological exhale. Volcanoes are constantly releasing carbon dioxide from Earth's interior back into the atmosphere. This CO2 is a potent greenhouse gas, trapping heat from the sun and warming the planet. Without this steady supply, our world would freeze over. But here is where the cycle reveals its brilliant balance. That same atmospheric carbon dioxide has a powerful interaction with water. It dissolves in rainwater, forming a weak carbonic acid. This slightly acidic rain falls upon the continents and begins a slow, patient attack on the very mountains that volcanism built. It chemically reacts with silicate rocks, the most common minerals in continental crust, breaking them down in a process called chemical weathering. The mountains literally dissolve, grain by grain, over millions of years. The products of this weathering, dissolved ions like calcium and bicarbonate, are then carried by rivers on an epic journey to the sea. Once in the ocean, microscopic marine organisms such as plankton eagerly absorb these dissolved chemicals. They use them as building blocks to construct their own protective shells and skeletons from calcium carbonate. This is a crucial transfer, moving carbon from the water into living and then solid form. When these tiny organisms die, their calcium carbonate shells rain down onto the deep ocean floor, accumulating as vast sediments. This is the planet's way of burying carbon. And the cycle completes its grand loop through the relentless engine of plate tectonics. The oceanic plate, laden with this carbonate-rich sediment, slowly drifts toward a subduction zone. There, it dives back into the mantle, carrying the locked-away carbon on a one-way trip into the planet's interior. Over millions of years, that carbon may be stored deep within the Earth, or it may be reheated and released once again through a future volcanic eruption, ready to begin the cycle anew. This self-regulating loop is a planetary feedback system of astonishing elegance. If the planet gets too warm, increased rainfall and warmer temperatures accelerate the weathering of rocks, pulling more CO2 out of the atmosphere, which in turn cools the planet down. If the planet cools too much, weathering slows, allowing volcanic CO2 to build up and warm the world again. For hundreds of millions of years, this geological heartbeat has maintained a climate stable enough for life to not just exist, but to thrive and evolve. The very ground beneath our feet, shaped by fire, is in a constant, slow dance with the air we breathe, a partnership written in stone and sky. The final proof of this ancient story is locked inside the tiniest of crystals. These are zircons, minerals tougher than almost anything else on Earth. While the original rocks of the primordial continents have long since eroded away or been recycled, these microscopic survivors endure. A zircon crystal can withstand billions of years of heat, pressure, and chemical attack, acting as a perfect, sealed time capsule from the planet's infancy. Geologists hunt for these grains like detectives searching for clues at a crime scene billions of years cold. By analyzing the minute amounts of uranium and lead trapped within their crystalline structure, they can pinpoint the exact moment the zircon crystallized from a cooling magma, providing a precise birth certificate. But the story does not stop with age. The very chemistry of these ancient crystals holds a revelation. Some of the oldest zircons ever discovered, from the Jack Hills in Australia, date back an astonishing 4.4 billion years. Their chemical signature tells us something profound. They formed from a magma that had interacted with older, continental-type crust. Even more telling, the oxygen isotopes within them suggest they crystallized in the presence of liquid water. This single piece of evidence rewrites our understanding of the early Earth. It suggests that continents and oceans, the fundamental stages for life, may have appeared incredibly soon after the planet's violent formation, transforming the image of the Hadean Aeon from a hellish wasteland into a world where the first seeds of land were already taking root. Zircons are not the only witnesses. Ancient lava flows, preserved in the few remaining scraps of the earliest crust, carry a magnetic memory. As the lava cooled, tiny magnetic minerals within it aligned themselves with the Earth's magnetic field, freezing a compass direction in stone. By reading this fossil magnetism, scientists can determine the latitude at which the rock formed, piecing together the drift of ancient continents across the globe. Other chemical tracers in these rocks act like fingerprints, revealing the depth and temperature at which the magmas were generated, telling us about the specific fiery processes that were operating deep within the young planet. Together, these geological time capsules form a forensic record, a scattered archive that allows us to reconstruct the epic of our world's creation. They are our direct link to the primordial fires, offering tangible evidence that the planet's breath has been building this land for almost its entire existence. The very same forces that build continents carve the pathways of life itself. A new mountain range is more than a wall of rock. It is a biological barrier that can divide a single species into two. When populations are separated by a newly risen chain of volcanoes or a widening ocean basin, their evolutionary paths begin to diverge. Over generations, isolated from one another, they adapt to their unique environments, slowly transforming until they can no longer interbreed. This process, known as allopatric speciation, is one of evolution's most powerful engines. The planet's fiery breath does not just create land, it creates the conditions for an explosion of new life forms. A perfect example of this is written in the narrow strip of land connecting North and South America. For millions of years, the Isthmus of Panama did not exist. The two continents were separated by a broad seaway, and life evolved in complete isolation on each landmass. South America was an island continent, home to bizarre marsupials and unique giant ground sloths. North America had its own cast of characters, including early horses and saber-toothed cats. Then, around 3 million years ago, volcanic activity and the slow collision of tectonic plates finally sealed the gap, lifting the Isthmus of Panama from the sea. The biological consequences were immediate and profound. In the oceans, species that had once mingled were now cut off. Creatures in the Atlantic and Pacific began their separate evolutionary journeys, leading to the distinct marine life we see in each ocean today. On land, the event triggered the Great American Biotic Interchange. Animals from the north, like deer, bears, and jaguars, marched south. Animals from the south, including armadillos, opossums, and giant ground sloths, moved north. This massive mixing of fauna reshaped entire ecosystems, a direct result of a geological event. But the influence of volcanic chains goes beyond just moving animals around. The landscapes they create become cradles for new life. The rich, nutrient-dense soils born from weathered volcanic ash are some of the most fertile on Earth. They allow pioneering plants to establish themselves quickly, forming the base for complex food webs. From the slopes of the Andes to the islands of Indonesia, these fertile volcanic regions are often hotspots of biodiversity, supporting a stunning variety of species found nowhere else. The map of life we see today, with its unique creatures on every continent, is a direct reflection of the planet's deep geological history. The fire that built the world also painted it with life. Iceland rises from the North Atlantic like a geological prophecy fulfilled. This is not merely an island, but a living, breathing demonstration of the planet's creative power in real time. The entire nation sits directly atop the Mid-Atlantic Ridge, the colossal undersea mountain range where the North American and Eurasian plates are slowly, inexorably tearing away from each other. In the gap that opens between them, magma from the mantle below wells up, constantly forging new crust. This is the fundamental process that builds the ocean floor all around the world, but Iceland is special. The ridge here is supercharged, situated directly over a powerful mantle plume, a deep-seated hotspot. This combination of forces makes the volcanism exceptionally prolific, piling up so much lava that it has built a landmass high enough to break the ocean surface. Iceland is in essence a piece of the mid-ocean ridge lifted into the open air. It is our planet's most dramatic and accessible window into the very process of crustal generation. Here, you can literally stand between two continents, with one foot on the North American plate and the other on the Eurasian plate, and watch the ground slowly widen over a human lifetime. Fissures rip open the earth, and volcanoes like Hekla and Eyjafjallajökull regularly remind the world of the fire that built them. This ongoing construction provides a tangible, small-scale model of the very same processes that, on a much grander scale and over hundreds of millions of years, built the first protocontinents. The volcanic ridges and vast plateaus formed at these divergent boundaries are the raw materials of the Earth. When these buoyant fragments are pushed by tectonic forces toward a waiting continent, they cannot be subducted. Instead, they are scraped off and accreted, welded onto the continental margin as a permanent new piece of land. Iceland shows us the foundry where the planet's foundation is cast, a continuous, fiery exhale that has been building our world from the very beginning. The relentless drift of the continents is a journey with no final destination. The ground beneath our feet is in constant, slow-motion travel, and by tracing its current path, we can map the future of our world. The Atlantic Ocean is still young and vigorous, its mid-ocean ridge actively forging new seafloor, pushing the Americas further away from Europe and Africa. Meanwhile, the mighty Pacific Ocean is in decline. Its oceanic crust, old and dense, is being consumed by the ring of fire's subduction zones faster than new crust can be created. It is slowly but surely closing, shrinking with every passing century. These opposing motions set the stage for a planetary-scale collision already underway. Africa is plowing northward into Europe, a slow motion crash that is squeezing the Mediterranean Sea out of existence. In its place, a new mountain range is being born, a future Himalayan-scale wall of rock that will one day stretch from Spain to Iran. To the east, Australia is a continent on a direct northerly heading, destined to plow into the islands of Southeast Asia and be sutured onto the Eurasian landmass. This continental dance, if allowed to continue for 250 million years, points to an inevitable conclusion. The scattered fragments of our world will reunite. Many geologists foresee the birth of a new supercontinent, a landmass they call Pangea or Pangea Proxima. In this future world, the Americas will have swung across the globe to fuse with a combined Eurasia and Africa, closing the Arctic Ocean in the process and creating a single, vast continent encircling what remains of the Indian Ocean. This is not science fiction, but the straightforward extrapolation of forces we can measure today. The same volcanic chains that built our continents will continue to forge new land at the seams of these titanic collisions. The planet that breathed fire in the past is still breathing, its deep, fiery rhythm continuing to write the next chapters in the epic story of our world. This same fire that built our world also filled its vaults. The geological forces that forged the continents over billions of years did more than just create land. They acted as nature's master alchemist, concentrating the very minerals that power our modern civilization. The intense heat and pressure of magmatic activity are a perfect recipe for sorting the Earth's scattered elements, pulling valuable metals from common rock and depositing them in rich, mineral veins. A stunning example of this is the porphyry copper deposit. These are not localized pockets of ore, but colossal, mountain-sized systems that supply nearly half of the world's copper, a metal essential for everything from electrical wiring to renewable energy. Their formation is a direct consequence of subduction. As a massive magma chamber cools miles beneath a volcanic arc, it releases superheated, mineral-rich fluids. These fluids are under immense pressure, forcing their way into countless tiny fractures in the surrounding rock. As they cool, they deposit their metallic cargo, creating a vast, diffuse network of copper-bearing minerals. This is why some of the world's largest copper mines are found along the volcanic spines of the Andes and the Rocky Mountains, places where this ancient, fiery plumbing system is now exposed at the surface. But the story of geological wealth stretches beyond these active margins. The single greatest source of gold ever discovered, the Witwatersrand Basin in South Africa, tells a different but equally fiery tale. Its origins lie in an ancient world over 2 billion years ago. The prevailing theory suggests that towering volcanic mountains, much like the modern Andes, eroded over millions of years. Rivers carried the gold, along with other heavy sediments, down into a massive basin. Then, tectonic forces, the same ones that assemble continents, warped and heated this basin, sealing the gold into incredibly rich conglomerate layers. This was not a sudden event, but a slow, geological accumulation followed by a tectonic locking in, a treasure chest created by the planet's relentless activity. Our search for these resources is, in essence, a search for understanding this deep geological history. Prospectors and geologists are reading the clues left by ancient subduction zones, mantle plumes, and continental collisions. The very copper in the walls of your home and the gold in a piece of jewelry are direct links to the planet's volatile past, a tangible inheritance from the volcanic fires that built the ground beneath our feet. Our ancestors felt the primal rumble deep in their bones. Long before we understood subduction or mantle plumes, human cultures crafted powerful stories to explain the mountains that breathed fire and the ground that shook. For the Romans, the violent tremors and fiery glow of Mount Etna were not random events. They were the hammer strikes of Vulcan, the god of fire, toiling in his subterranean forge. Each eruption was the bellows of his workshop, each spark from his anvil a piece of incandescent rock flung into the sky. He was a creator, crafting weapons for the gods, but his power was also a constant, terrifying presence for those who lived in the volcano's shadow. Half a world away, the Hawaiian people saw a different but equally potent force in their volcanoes. They told stories of Pele, a passionate and powerful goddess whose mood dictated the very creation and destruction of the land. When she was calm, she would build new islands with gentle flows of lava. But when her legendary temper flared, the earth would split open and rivers of fire would consume everything in their path. The landscape itself was seen as evidence of her travels and her battles, a testament to her volatile, creative spirit. These myths were far more than simple fables. They were humanity's first geological theories, a way to rationalize the terrifying and awesome power of a living planet. They personified the forces of eruption and earthquake, giving them names, faces, and motivations. This deep-seated need to find meaning in the chaos reveals a fundamental truth. Our fascination with the planet that breathes fire is as ancient as storytelling itself, a timeless recognition that the ground we build our lives upon is anything but silent or still. These hidden processes are no longer just theoretical. We can now see them with our own eyes, or rather, with the sophisticated senses of modern technology. Uncovering the secrets of how volcanic chains built the continents requires us to look deep beneath the surface, to map the very engine of the planet. One of the most powerful tools for this is seismology. It uses the immense energy released by earthquakes as a planetary-scale ultrasound. When the ground shakes anywhere in the world, it sends seismic waves pulsing through the entire Earth. By tracking the speed and path of these waves with a global network of sensitive detectors, scientists can create stunningly detailed three-dimensional images of the interior. These tomographic maps reveal the cold, dense slab of a subducting plate diving hundreds of miles into the mantle. They illuminate the rising pillars of superheated rock that form mantle plumes. They can even outline the vast, hidden magma chambers that feed volcanic chains, showing us the plumbing system of the continents in real time. While seismology shows us the deep structure, another technology tracks the surface motion with breathtaking precision. Satellite-based GPS systems measure the slow, constant drift of the tectonic plates. They can detect movements as slight as a few millimeters per year, confirming that North America and Europe are inching further apart, that India is still plowing into Asia, and that the entire Pacific Ring of Fire is in a state of continuous, measurable compression. This is not guesswork, it is a live broadcast of continental construction. Other methods fill in the rest of the picture. Gravity mapping satellites detect tiny variations in the Earth's gravitational field. These anomalies reveal where mass is concentrated underground, helping to identify dense ancient cratons or the lighter roots of young mountain ranges. Meanwhile, a technique called magnetotellurics measures how naturally occurring electrical currents from the sun and our planet's magnetic field penetrate the ground. Since different rocks have different electrical conductivities, this method can pinpoint bodies of water-saturated rock or massive ore deposits, tracing the fluid pathways that are so crucial to creating magma. Together, this suite of tools has completely transformed geology. It has taken us from a science that studied surface rocks to one that can conduct a full body scan of the entire Earth system. The theories of subduction, accretion, and mantle plumes are no longer just elegant ideas. They are now observable, measurable realities. These technologies provide the hard data that confirms the epic story written in fire and stone, allowing us to witness the planet's fiery breath as it continues to shape our world. Alfred Wegener's idea of drifting continents was brilliant, but it was a theory without an engine. He saw the puzzle piece fit of the continents. He found matching fossils on opposite shores of the Atlantic, but he could not answer one simple, devastating question. What force could possibly shove entire landmasses through the solid rock of the ocean floor? Without a mechanism, his grand vision of continental drift was dismissed as geological fantasy for decades. The breakthrough did not come from the continents at all, but from the dark, unexplored world at the bottom of the sea. In the years following World War II, new technologies like sonar began to map the ocean basins, revealing a landscape more dramatic than anyone had imagined. Scientists discovered a continuous, submerged mountain range winding through every ocean, a global seam 40,000 miles long. Even more astonishing, they found that the ocean floor was youngest right at the crest of these mid-ocean ridges and grew progressively older with distance. This was the key. The seafloor was not a static, ancient plain. It was being created right then from the mantle below. Molten rock was rising at the ridges, solidifying into new oceanic crust, and then being pushed slowly aside to make room for even newer crust. This process, called seafloor spreading, was the missing mechanism. It was the conveyor belt Wegener never found. But a conveyor belt needs a sinkhole, a place where the old material is consumed. That place is the deep ocean trench. As new crust forms at the ridges, old, dense crust is pulled back down into the mantle at subduction zones, completing the cycle. This discovery was confirmed by another line of evidence, locked in the magnetic memory of the seafloor. As volcanic rock cools, tiny magnetic minerals within it align with the Earth's magnetic field, freezing its direction in time. Scientists found that the ocean floor was striped, with parallel bands of rock recording normal and reversed magnetic polarity, perfectly mirrored on either side of the mid-ocean ridge. This magnetic tape recording was undeniable proof that the seafloor was spreading, steadily unspooling from the ridge like a double-sided scroll. These separate threads, the fit of the continents, the mechanism of seafloor spreading, and the paleomagnetic proof, were finally woven together in the 1960s into the single, unifying theory of plate tectonics. This was not just an adjustment to geology, it was a revolution. It transformed our view of the Earth from a static, finished globe to a dynamic, living planet. It explained not only why South America and Africa fit together, but why earthquakes shake Japan, why volcanoes crown the Andes, and why the Himalayas rise toward the sky. For the first time, we had the master blueprint for the planet's endless, fiery construction site. Our planet's fiery creativity appears to be a rare masterpiece in the cosmos. As we identify thousands of worlds orbiting distant stars, we are forced to ask if Earth's particular style of geology, the very process that built our continents, is a cosmic fluke. Look no closer than our own solar system for a sobering comparison. Venus is often called Earth's twin, a world of similar size and composition. It is covered in vast volcanic plains, clear evidence of a fiery past. Yet Venus shows no signs of the plate tectonics that constantly reshape our world. Instead, it operates under what scientists call a stagnant lid regime. Its crust forms a single, unbroken shell that traps the planet's internal heat like a thick blanket. Without the release valve of moving plates, this heat builds until the entire lid catastrophically melts and resurfaces the planet in a single, global volcanic event. This stifling geological cycle is intimately linked to its atmosphere, a crushing hellscape of carbon dioxide that traps solar energy and creates a runaway greenhouse effect, rendering the surface hot enough to melt lead. The absence of our planet's recyclic tectonic system seems to be a key ingredient in that planetary disaster. Then there is Mars, a world that presents a different kind of volcanic story. It is home to Olympus Mons, the largest volcano in the solar system, a mountain that dwarfs anything on Earth. This titan is a monument to what is known as single-spot volcanism. A massive mantle plume burned through the Martian crust, and because the plate above it never moved, it simply kept pouring lava out of the same vent for billions of years, piling up into a colossal but isolated peak. Mars lacks the mobile plates that would have spread this volcanic output into a chain of islands or a mountain range, the fundamental building blocks of a continent. Its geology is static, its landscapes largely frozen in time. This cosmic comparison brings Earth's special recipe into sharp focus. Our planet's particular combination of size, which provides just enough internal heat to keep the engine running, its unique composition, and most critically, the presence of liquid water, create the perfect conditions for the dynamic, recyclic process of plate tectonics. Water lubricates the grinding plates and, as we have seen, is the essential catalyst that allows the mantle to melt and generate the granite of continents. This dynamic system does not just build land, it recycles it, regulates global temperatures, and maintains the habitable world we know. The vibrant, diverse continents we call home are not a universal given. They are the magnificent and perhaps singular product of a very specific and very fortunate planetary fire. Our journey ends where it began, with the fire beneath our feet. We have traveled across 4.5 billion years, from a global ocean of molten rock to the familiar shapes of our modern continents. We have witnessed the planet's first breath of water and air, felt the slow churn of its mantle engine, and stood at the edge of subduction zones where new land is forged from the abyss. This is the legacy of the volcanic chains, the great architects of our world. They built the unshakable cratons, expanded the continents piece by piece through relentless accretion, and even triggered the very climate cycles that keep our planet alive. This story binds the deepest mantle plume to the highest mountain peak, the oldest zircon crystal to the newest island breaking the waves in Iceland. It connects the most devastating extinctions with the most spectacular explosions of life, reminding us that creation and destruction are two faces of the same planetary force. The ground you stand on is not a passive stage, but the active, breathing surface of a living world. We are merely temporary guests on this ever-changing landscape, a landscape that is still being written by the planet's fiery heart. So the next time you feel the solid earth beneath you, remember the epic journey it represents. See the world not as a finished map, but as a single, dynamic frame in a story billions of years in the making, and let that inspire you to keep exploring the incredible, ongoing saga of our planet.